Hello everybody. Good morning. Myself, Dr. Shubhankar Sen, an associate professor in the Department of Mechanical Engineering, IIT ISM Dhanbad, welcome you to the fourth lecture of the third module of the 12-week SWAYAM NPTEL course, Finite Element Method in Thermal Engineering. In today's lecture, we shall illustrate the FEM discretization of one-dimensional Poisson equation of heat conduction using a bar element, and then we shall solve this problem subject to the essential boundary conditions at both the boundaries. We shall also compare the numerical results obtained from other discretization techniques such as finite difference and finite volume methods, and also with the analytical solutions. Now we go for the finite element solution of the same problem. So here the strong form is given by d2t dx2 plus 1 equals to 0 on omega, t equals to g1 equals to 100 degrees centigrade on gamma g1, and t equals to g2 equals to 50 degrees centigrade on gamma g2. So here this is the rod. So this boundary is gamma g1, this boundary is gamma g2, this is x equals to 1, this is x equals to 0, here t equals to 100 degrees centigrade, here t is 50 degrees centigrade. The governing equation is k d2t dx2 plus q equals to 0 on omega, where k equals to 1 watt per meter degree centigrade and q equals to 1 watt per meter cube. So the first step in the finite element solution is the formation of the weighted integral statement by using the method of weighted residuals. So here the residual for this problem is Rx equals to d2th dx2 plus 1. This statement of method of weighted residual or MWR gives integration over omega Wx Rx d omega equals to 0. Now we discretize our domain into 5 finite elements. So these are the global nodes. Global node 1, 2, 3, 4, 5 and 6. Our elements are 1, 2, 3, 4, 5. So this is in the mesh size as delta x equals to 0.2. Delta x equals to 0.2 is uniform. At the element level, MWR is expressed as integration over omega e Wx Rx d omega e equals to 0 integration over omega e Wx, here our Rx is d2th dx2 plus 1 d omega e equals to dx equals to 0. So this is an arbitrary finite element with local nodes 1 and 2. The mesh size is denoted by the symbol delta x, and then this MWR statement for the element, it gives us as integration over omega e w d2th dx2 dx plus integration over omega e w dx equals to 0. Now d omega e equals to dx, the element dimension, and then by integrating by parts and dropping the superscript h, we get minus integration over omega e gradient of w dot gradient of t d omega e plus integration along the boundary gamma e w into dt dx d gamma e plus integration over omega e w dx equals to 0. Now, for the present problem, both BC's boundary conditions are of EBC type. At the essential boundary, W equals to 0. So, at the essential boundary, the weight function satisfies the homogeneous part of the essential boundary condition. Because of that, we get that the natural boundary condition term or the flux term W dt dx d gamma e, it vanishes for this problem. So this is the NBC term, and this form is known as the weak form of the given strong form. So the equation simplifies to minus integration over omega e gradient of w dot gradient of t dx plus integration over omega e w dx equals to 0. This gives us integration over omega e gradient of w dot gradient of t dx equals to integration over omega e w dx. Now, in the left hand side, now we have the bilinear form bw comma t, and the right hand side we have the linear functional L of w Now, this term, we can go for the further simplification with the use of Galerkin formulation. Here, this is the element with mesh size delta x. This is the x direction. This is the origin of the coordinate system. So this distance, the global coordinate of this local node 1, this is x1e, and the global coordinate of local node 2, this is x2e. So we already know that x2e equals to x1e plus delta x. Now the weak form bwt equals to lw, it can be further simplified in one dimension as b Wt equals to Lw. Now Bw comma T equals to Lw is simplified as integration. Now this is our omega E, which is varying from x1e to x2e in one dimension. Gradient of W dot gradient of T, it becomes dw dx into dt dx equals to integration of x1e to x2e w dx. Now we introduce the trial solution and the Galerkin approximation. For diffusion dominated problems, use GFEM or Galerkin's approximation, which gives us Wx equals to psi IEx. So weight function, it becomes equal to the shape function at the ith node, and we have the trial solution. The trial solution for temperature is given by Tx equals to summation of Tje psi je, where j is varying from 1 to nen. So j equals to 1 to nen. This is the unknown part of the trial solution, and then we have from the known part of the trial solution. So that is summation of Tbe psi be x, where b belongs to eta g, or b belongs to the essential boundary. Now we can simplify the weak form further, putting Wx equals to psi Iex and Tx equals to summation of Tje psi Jex, j equals to 1 to nen, plus summation of Tbe psi Bex, where b belongs to eta g, in integration from x1e to x2e dw dx dt dx equals to integration x1e to x2e w dx. We obtain integration x1e to x2e, w is psi ie, d psi ie dx ddx of summation of Tje psi je, j equals to 1 to nen, plus summation of Tbe psi be, b belongs to eta g, dx equals to integration from x1e to x2e psi ie dx. From here we can further simplify it as summation over j equals to 1 to nen d psi ie dx, integration from x1e to x2e d psi je dx into Tje, plus summation over b belongs to eta g, integration over x1e to x2e d psi ie dx d psi be dx Tbe equals to integration of psi ie dx from x1e to x2e. Now in the left hand side, the contribution from the essential boundary condition makes the second term as known. And then this is shifted to the right side and shifted to the RHS. So we get, after further simplification, as summation j equals to 1 to nen integration from x1e to x2e d psi ie dx d psi je dx dx tje equals to integration of psi ie dx from x1e to x2e minus summation over b belongs to eta g integration from x1e to x2e d psi ie dx d psi be dx dx tbe. This can be simplified further as summation over j equals to 1 to nen k ije tje equals to integration over psi ie dx from x1e to x2e minus summation of b belongs to eta g k ibe tbe equals to fie, where k ije equals to integration from x1e to x2e d psi ie dx d psi je dx dx k ibe equals to integration from x1e to x2e d psi ie dx d psi be dx dx and fie equals to integration from x1e to x2e psi ie dx minus summation over b belongs to eta g k ibe tbe. Now this algebraic equation which we obtained at the end, this can be rewritten again as summation of j equals to 1 to nen k ije equals to fie or k ije equals to fie the element level matrix equation system obtained after GFEM or Galerkin FEM discretization. Now this Kije, this expression was given as integration from x1e to x2e d psi ie dx d psi je dx dx. Here we have a two-noded bar element, so I is varying from 1 to 2, j is varying from 1 to 2, and our number of element nodes equals to 2 for this particular case. Now we have already seen the correspondence between the local and global coordinate system. So here this is the origin of the global coordinate system. With respect to the global coordinate system, these coordinates are x1e and x2e. This is the origin of the global coordinate system. Now, the local coordinate system is such that x bar equals to 0 at the first local node of any element, and x bar equals to delta x of the second local node of the same element. So, the correspondence between the local and global nodes for one-dimensional problems using bar elements, we already know that x equals to x bar plus x1e. This is the transformation formula where x is the global coordinate and x bar is the local coordinate. So, using this transformation relation, this is a linear coordinate transformation. This transformation helps us to perform the integration when x equals to x1e, then x1e equals to x bar plus x1e. This gives x bar equals to 0. When x equals to x2e, x2e equals to x bar plus x1e gives x bar equals to x2e minus x1e. So this is delta x. So this kije, it can be written as x1e, this is 0 in the local coordinate, and x2e, this is delta x in the local coordinate system. d psi ie x dx equals to d psi I x bar dx bar dx bar dx. From this coordinate transformation, we find that dx equals to dx bar plus 0 equals to dx bar. So, dx equals to dx bar. This gives us, this is equal to d psi ie x bar dx bar, since dx equals to dx bar. So, this can be written as d psi ie x bar dx bar d psi je x bar dx bar dx bar. Now, our psi 1e x equals to x2e minus x by delta x. This is equals to x2e minus x equals to x bar plus x1e, x bar minus x1e by delta x equals to x2e minus x1e minus x bar by delta x. So this is delta x minus x bar by delta x equals to 1 minus x bar by delta x, and psi 2e x bar, this is x minus x1e by delta x. This is x bar plus x1e minus x1e by delta x. So this is x bar by delta x. So now the Lagrangian shape functions in the global coordinate system psi 1e and psi 2e, when we represent in terms of the local coordinate system x bar, then the expressions we have psi 1e x bar, this is equals to 1 minus x bar by delta x, and psi 2e x bar equals to x bar by delta x. So now we evaluate the entries of the element level matrix equation, then the entries of the element level matrix are obtained as k ije equals to integration from 0 to delta x d psi ie x bar dx bar d psi je x bar dx bar, where psi 1 e x bar equals to 1 minus x bar by delta x and psi 2 e x bar equals to x bar by delta x. They satisfy the conditions of Lagrangian shape functions. Now, if we put, so from here we can see that for I equals to 1 to 2 and j equals to 1 to 2, this KE, it becomes a 2 by 2 matrix equation system. Okay, so when I equals to 1 and j equals to 1, we get K11E. K11E equals to 0 to delta x d psi 1e x bar dx bar. Again here d psi 1e x bar dx bar. So d psi 1e x bar dx bar whole square dx bar. So d psi 1e x bar dx bar, this is minus 1 by delta x. So minus 1 by delta x whole square dx bar. So this is 1 by delta x whole square integration 0 to delta x dx bar equals to 1 by delta x whole square into delta x equals to 1 by delta x. When I equals to 1 and j equals to 2, we get K12E as integration 0 to delta x d psi 1e x bar dx d psi 2e x bar dx bar equals to integration of 0 to delta x d psi 1e x bar dx bar equals to minus 1 by delta x and d psi 2e dx bar equals to 1 by delta x dx bar equals to minus 1 by delta x whole square integration 0 to delta x dx bar. This gives us minus 1 by delta x whole square into delta x equals to minus 1 by delta x. When I equals to 2 and j equals to 2, K21E equals to integration 0 to delta x d psi 2e x bar dx bar d psi 1e x bar dx bar equals to K12E equals to minus 1 by delta x. And finally, for the last term in the 2 by 2 matrix, when I equals to 2 and j equals to 2, we get K22E equals to integration 0 to delta x d psi 2e x bar dx bar and d psi 2e x bar dx bar again. So we get here the whole square of d psi 2e dx bar. This simplifies as 0 to delta x d psi 2e x bar dx bar is 1 by delta x whole square. So this is 1 by delta x whole square dx bar equals to 1 by delta x whole square into x bar varying from 0 to delta x. So this is 1 by delta x. So now we have calculated all the components of the element level coefficient matrix. So it is given as Ke equals to K11E, K12E, K21E, K22E. Here K11E, it was 1 by delta x. K12E was minus 1 by delta x. K21E, it was minus 1 by delta x. And K22E, it is 1 by delta x. Okay, so our delta x was 0.2. So this is 1 by 0.2 minus 1 by 0.2 minus 1 by 0.2, 1 by 0.2. So this gives us, this is 1 by 0.2 means it is 5, minus 5, minus 5, and then this is 5. Now, if you look into this matrix, this element level matrix, it is a singular matrix. Its determinant is 0 valued. It means that the rows of this matrix and columns of this matrix is linearly dependent. Okay, so we note this. Ke is a singular matrix. Its rows and columns are linearly dependent. This we have already told in the first class of this course, but when we assemble the element level coefficient matrices, then the assembled matrix, it becomes a linearly independent matrix, and because of that only we are able to get a unique solution. Okay, so now we have the Ke terms. Let us now go for the Fe terms. So if we go for the load vector at the element level, these were Fe equals to integration x1e to x2e psi ie, this was Fie, psi ie dx minus summation over b belongs to eta g integration from x1e to x2e. This is d psi ie dx d psi be dx dx tbe. Now this first part, this is contributed by the source term. The second part is contributed by the EBC term. So this is equals to from x1e to x2e by psi ie dx minus summation over b belongs to eta g k ibe tbe. Now k ibe terms are already computed while computing the Ke or Kij matrix. Therefore, we only compute the contribution of source term to Fie. So Fie, this is the element level load vector. Since Kibe belongs to Kij, we only compute the role of source term in Fie. So therefore, Fie equals to integration of psi ie dx from x1e to x2e. Now we have already shown the correspondence between the local and global coordinates in one dimension. So we simply substitute x by x bar in the right hand integrand. It gives us from 0 to delta x psi ie x bar dx bar. So for the element level vector, the load vector Fe, it is containing two entries, F1e and F2e. It is a 2 by 1 vector. So I is varying from 1 to 2. F1e equals to from 0 to delta x psi 1e x bar dx bar equals to integration from 0 to delta x 1 minus x bar by delta x dx bar equals to integration of 0 to delta x dx bar minus integration 0 to delta x bar by delta x dx bar. This is equals to x bar varying from 0 to delta x minus 1 by delta x bar whole square by 2 varying from 0 to delta x equals to delta x minus delta x by 2. So this is delta x by 2. Similarly, f2e equals to integration from 0 to delta x psi 2e x bar dx bar equals to integration 0 to delta x bar by delta x dx bar equals to 1 by delta x into x bar whole square by 2. Here the range is 0 to delta x, 1 by 2 delta x into delta x whole square. So this is delta x by 2. So our load vector, this is delta x by 2 per component. So it means the load vector Fe equals to delta x by 2, delta x by 2, 2 by 1 vector. Delta x was 0.2. So this is 0.1 and 0.1. Now we have our element level matrices and vector entries computed by direct integration. Okay. Now we construct the ID array and the LM array for the construction of the global matrix equation system and also to implement the boundary condition. So we generate the ID array. Now we have 6 global nodes. So this is element 1, element 2, element 3, element 4 and element 5. At the left and right boundaries, our equations are not required because we already have the solutions. So the equation number will be 0 at these 2 corners. So 0 and 0 in the remaining nodes, the global equation numbers are 1, 2, 3 and 4. These are the global equation numbers P and Q, and global node numbers are 1, 2, 3, 4, 5 and 6. So these are the global node numbers and these quantities are the element number. Now the ID array for a single degree of freedom problem, it is defined as ID of A equals to P. We generate the ID array as A versus ID of A. So here we have A is varying from 1 to 6, 1, 2, 3, 4, 5, 6. So here ID of A, it is going 0 and 0 for nodes 1 and 6. For nodes 2, 3, 4 and 5, the internal nodes, these numbers are 1, 2, 3 and 4. Now taking help of the ID array, we can generate the LM array. So LM array is defined as LM AE equals to P. So we generate it at E. This is A, this is I, this is NEE or A prime or B prime. So our elements were 5 in number, 1, 2, 3, 4, 5. Our local nodes are 1 and 2. Degree of freedom per node is 1. So number of element level equations, it is 2 equations per element. So these will be 1 and 2. These are 1 and 2. Now we fill the global equation numbers in these boxes. For the first element, the global equation numbers are 0 and 1. For the second element, the global equation numbers are 1 and 2. For the third element, these are 2 and 3. For the fourth element, these are 3 and 4. And for the fourth element, these are 4 and 0. So our maximum number of equations which we see in this LM array, this is 4. So we shall have a 4 by 4 global matrix equation system. Since capital P equals to 4, the assembled matrix equation system will be of size 4 by 4. Now, this matrix will be KT equals to F, the assembled matrix equation system, where KT will be K11, K12, K13, K14, K21, K22, K23, K24, K31, K32, K33, K34, K41, K42, K43, K44. Then we have here T1, T2, T3, T4. So here our right hand side is F1, F2, F3 and F4. So here if we plot the mesh again, this is 0, this is T1, this is T2, this is T3, this is T4, and finally this is equation number 0. These are the global equation numbers. So here we make the LM array once more, which shows us E, A, I, N, E, E. 1, 2, 1, 2, 3, 4, 5, 1, 1, 1, 2. So for the first element, our equation numbers were 0, 1. For the second element, they were 1, 2. For the third element, they were 2, 3. For the fourth element, they were 3, 4. And for the fifth element, they were 4, 0. Now, this KT equals to F system can be constructed as construct KT equals to F using the LM array. So here, this is the K matrix. So first term is K11. Now for K11, we easily understand that this will be K221 plus K112. Then we have K12. K12 will be K122. K13 is absent. K14 is absent. Now we go to K21. K21 equals to K12. So this will be K212. Then K22 will be K222 plus K113. K23 will be K123. K24 is 0. K31 does not exist in any element. The global numbers 3 and 1. So K31 is 0. K32 will be K213. K33 will be K223 plus K114. K34 will be K124. K41 is 0. K42 is 0. K43, this will be K214. And then K44, this is K224 plus K115. This is the assembled matrix. Then we have the unknown load vector, unknown degree of freedom vector, T1, T2, T3 and T4. Now the essential boundary conditions, they will affect only the nodes which are belonging to the boundary elements. So if we look into the mesh once more. 4, 5 and 6. So global equation number 1, 2, 3 and 4, and our elements are 1, 2, 3, 4 and 5. From this picture we understand that the elements 3, their nodes 2 and 3, they will not be affected by the boundary conditions. So the load vector for local nodes 2 and 3 of element 3 will be contributed only by the source term and not by the boundary condition. Now let us go for the F1 term. So F1 will be F21 plus F12. F2 will be F22 plus F13. F3 will be F23 plus F14, and F4 will be F24 plus F15. Now the first term, the first row, this will be affected by the essential boundary condition, and this term comes as, for the first equation, the EBC contribution will be minus KIBE TBE. Now for this case we are writing the governing equation. So here E equals to 1, we write the equation at the second local node. So I equals to 2 and B equals to 1 EBC node. So from here we shall subtract minus K IBE. So this I is 2, B is 1, E is 1 into TBE. Similarly, the same thing will happen for the last element or for the fifth element. So for E equals to 5, our I equals to 1 and B equals to 2, TB5 equals to 50 degrees centigrade, TB1 equals to 100 degrees centigrade. So here we shall subtract minus K IBE TBE 1 to 5 TB5. In this case it will be TB1. So now we have made the terms that will construct the global matrix equation system and load vector. So here we get our element level matrix equation was KETE equals to FE. So it was 5 minus 5 minus 5 5 T1E T2E. This was delta x by 2 0.1, delta x by 2 0.1. So K221, 22 means 5, so this will be 5 plus K112, 112 is again 5, K12, this is minus 5, so this is minus 5, then this remaining zeros. In the second row, K21, K21 is minus 5, K222, it is 5 plus K113 again 5, so this is 5 plus 5. Then K12 is minus 5, next is 0. In the third row it is 0, K21 it is minus 5, K22 is 5 and K11 is again 5, so it is 5 plus 5. The K124, K12 is minus 5, so it is minus 5. In the last equation 0, 0, K214, 21 is minus 5, K224 plus K115, both are 5 plus 5, so 5 plus 5. Then we have T1, T2, T3, T4. Now, in the right side, we are getting F11, F21 plus F12. F21 and F12 both are 0.1. So it is 0.1 plus 0.1 minus K211. K211 is minus 5. So into 100. This is the TB1. So F22 plus F13, there will be 0.1 plus 0.1. Same will happen at the bottom, 0.1 plus 0.1. Then for the fourth row, we have 0.1 plus 0.1 minus K125 is minus 5 and TB5 is 50. So we have 50. Now, if we just combine this, we get the final matrix equation system as 10 minus 5, 0, 0, minus 5, 10, minus 5, 0, 0, minus 5, 10, minus 5, 0, 0, minus 5, 10. Then we are left with T1, T2, T3, T4 equals to 500.2, 0.2, 0.2. This is 250.2. So if we divide by 5 on both sides, we shall get 2, minus 1, 0, 0, minus 1, 2, minus 1, 0, 0, minus 1, 2, minus 1, 0, 0, minus 1, 2, T1, T2, T3, T4 equals to 100.04, 0.04, 0.04 and 50.04. So this is the same matrix equation system that we have obtained using the finite difference method or the finite volume method. Solving this matrix equation system, our solution becomes T1 equals to 90.08 degrees centigrade, T2 equals to 80.12 degrees centigrade, T3 equals to 70.12 degrees centigrade, and T4 equals to 60.08 degrees centigrade. So therefore, it is found that for the 1D Poisson equation of heat conduction, FDM, FVM and FEM using two noded bar elements yield identical solutions. Here we compare the exact and numerical solutions as exact numerical. Under numerical we have FDM, FVM and FEM. So we have 6 temperatures, T1 and T6. They were given 100 degrees centigrade and 50 degrees centigrade. So these are 150 degrees centigrade. So we have the computed quantities T2, T3, T4 and T5. So T2 was 90.08 degrees centigrade. By all the methods, we get exactly the same value, 90.08 degrees centigrade. T3 is 80.12 degrees centigrade. Numerical method also gives T3 as 80.12 degrees centigrade. T4 is 70.12 degrees centigrade. Here also we get 70.12 degrees centigrade. Finally, T5 was 60.08 degrees centigrade. We get 60.08 degree centigrade. So therefore, the analytical solutions exactly matches with the computational solutions. If we plot the temperature distribution here as Tx versus x, then we find that this is x equals to 0, this is x equals to 1. So we have node 2, node 3, node 4, node 5, and finally the boundary node. So we get a parabola. So if we plot these values, so this temperature is 100 degrees centigrade. This temperature is 50 degrees centigrade. Then we have 90 degrees centigrade, 90.08 degrees centigrade. Then we have at node 4. Then we have at node 5. So this is a parabolic curve. So this is node 2. This is T2, T3, T4, T5. Right hand side boundary is T6, left hand side boundary is T1. So this is the distribution of the temperature. So temperature is decreasing in a parabolic fashion. Now we can construct the curve for the heat flux within every element. We know that the temperature gradient is dt dx equals to dt x bar dx bar dx bar dx. Since dx bar equals to dx, we can write dt dx equals to dt x bar dx bar. Now tx bar equals to summation of tj psi j x bar, j varying from 1 to nen. So our nen is 2 here for the 2-noded element. So this is T1e psi 1e x bar plus T2e psi 2e x bar equals to T1e into 1 minus x bar by x plus T2e into x bar by delta x. So it will be delta x. So these distances are delta x. So we can see that here in this picture at the inter-element boundaries the temperature is continuous. So we say that T is C0 continuous. So we get piecewise continuity of temperature solution. At the boundary of every element, the temperature is matching, and then temperature has only unique value at the junction. This is the property of a C0 continuous function. Now we shall see that how the temperature gradient changes. So it should be discontinuous. That we know the temperature gradient for Lagrangian elements becomes discontinuous. So we shall try to show it now here. So if we use dt x bar dx bar, this gives us minus t1e into 1 by delta x plus t2e into 1 by delta x. So it is t2e minus t1e by delta x. Therefore, heat flux in an element equals to minus k dt dx. So this is equals to minus k into T2e minus T1e by delta x. So this is equals to T1e minus T2e by delta x. So now we have the expression for the heat flux. Therefore, heat flux in an element equals to minus k dt dx equals to T1e minus T2e by delta x. Now we have the temperature solutions. So these temperatures were T1 equals to 100 degrees centigrade, T2 equals to 90.08 degrees centigrade, T3 equals to 80.12 degrees centigrade, T4 equals to 70.12 degrees centigrade, T5 equals to 60.08 degrees centigrade, and finally T6 equals to 50 degrees centigrade. For element 1 or E equals to 1 minus k dt dx equals to T11 minus T21 by delta x. So this should be 100 minus 90.08 divided by 0.02. So this will be 9.92 divided by 0.02. For E equals to 2 minus k dt dx equals to T12 minus T22 by delta x. So T12 is here 90.08 and T22 is 80.12. T12 is 90.08 and T22 that is T3 that is 80.12 and divided by 0.02. So we can find this value as so we can see that these two values, they are different, and particularly at element 2 this value is higher. So heat flux for element 2, it is of higher value than heat flux at element 3, element 1. Then if we go for element 3, for E equals to 3 minus k dt dx equals to T13 minus T23 by delta x. Delta x is 0.02 and T13 is 80.12 minus T23 is 70.12. So this is again going for 10 by 0.02. So this is again a higher value. It means that as we are moving towards right, the heat flux value, it is increasing. For E equals to 4 minus k dt dx equals to T14 minus T24 by delta x equals to 0.02. T14 is 70.12 and T24 is 60.08. So this is 10.04 divided by 0.02. So this is even higher. And finally, for E equals to 5 minus k dt dx equals to T15 minus T25 by delta x. Delta x is 0.02. T15 is 60.08 minus 50. So it is 10.08 divided by 0.02. So it means that for every element we got different values of dt dx, and in particular dt dx values are increasing as we are moving rightwards from the first element to the last element. If we plot the dt dx versus x here, then we can see here the left hand side is minus k dt dx, the y-axis, and right hand side is the x-axis. So we have node 1, equation number 0 for x equals to 0. Then we have, this is node 1, this is node 2, this is node 3, this is node 4, this is node 5, and finally we have node 6. So dt dx for node element 1, this is element 1, this is the value of minus k dt dx. We move for element 2. This is the value of minus k dt dx. We move for element 3. This is the value of representative picture for minus k dt dx within element 3. This is for element 4. And finally, we have for element 5. It means that dt dx value is constant within an element, but dt dx is discontinuous outside an element. This kind of continuity is known as c to the power minus 1 continuity. So we say that from the plot from the minus k dt dx versus x plot minus k dt dx or dt dx is constant within an element but discontinuous at element interfaces. These are c minus 1 continuous functions. There is an error. The value of mesh size, which I have been repeatedly speaking here as 0.02, it is actually 0.2. So I make this correction here. So this 0.2 throughout. So delta x is 0.2. And in this case, we have taken k equals to 1 unit. Let us consider that instead of the essential boundary, the right-hand boundary may be convective boundary, maybe Neumann boundary, or maybe the radiative boundary. So what will be the structure of the matrix vector equation system after assembly? Let us briefly illustrate this case. So we have the same problem. The bar is of 1 unit length. So this is the case of NBC, CBC, RBC at right boundary, EBC at left boundary. So left boundary, this is at x equals to 0. This is EBC, T equals to 100 degrees centigrade. Here x equals to 1. It can be NBC or CBC or RBC. For NBC, the value will be Q0 right. For CBC, the parameters of interest are H and T infinity. For RBC, the parameters of interest are epsilon, alpha, and sigma. Now, let us consider the NBC first. If we go for NBC, case 1, NBC. So, we have 5 elements, element 1, element 2, element 3, element 4, and element 5. Global nodes 1, 2, 3, 4, 5, 6. Left hand side is 100 degrees centigrade, right hand side is Q0R. So, element level matrix equation system is KET equals to FE, or we have K by delta x minus K by delta x minus K by delta x, K by delta x, T1E, T2E equals to F1E, F2E equals to delta x by 2, delta x by 2. This you already know. So this is a two-noded bar element. This is arbitrary element E, local nodes 1 and 2. This is T1E, this is T2E, and the mesh size is delta x. Now, if we construct the ID array for this ID array, then we get that at the sixth global node, the temperature is unknown for all three cases like NBC, CBC, and RBC. So at the left boundary, the equation number is 0, then equation number 1, 2, 3, 4, and 5. So A versus ID array. So A versus IDA, it gives us for nodes 1, 2, 3, 4, 5, 6. So here we get 0, 1, 2, 3, 4, and 5. So these are capital P, these are capital A, and these are the elements small e. We can construct the LM array also. This is E, this is A, this is I, this is N, E, E. E is varying from 1, 2, 3, 4, 5. A is 1 and 2, I is 1, 1. And any EE, this is varying from 1 to 2. So, for the first element, our equation numbers are 0 and 1. For the second element, our equation numbers are 1 and 2. For the third element, the equation numbers are 2 and 3. For the fourth element, these are 3 and 4. And finally, for the fifth element, we have equations 4 and 5. So, in both EBC cases, our matrix equation system was 4 by 4. Here we have an extra equation at the secondary variable boundary condition. So we shall get an enhanced matrix of 5 by 5 size. Therefore, the global matrix equation system is of 5 by 5 size. Okay, so here the assembled matrix equation system, the assembled matrix equation system looks like KT equals to F, where we have 5 unknowns, T1, T2, T3, T4, T5. Then this is F from source term. We know that the contribution is delta x by 2 plus delta x by 2. So in this case also, delta x by 2 plus delta x by 2. We have already done it for the EBC problem. Delta x by 2 plus delta x by 2. Delta x by 2 plus delta x by 2. And here also it is delta x by 2. So our LM array was like E 1, 2, 3, 4, 5, 1, 2, 1, 1, A, I, N, E, E, 1, 2. So these were 0, 1, 1, 2, 2, 3, 3, 4, and 4, 5. So at the fifth equation, our F5 will be F25. So F25 means it is having no addition. So here it is just delta x by 2 plus we have the contribution from the natural boundary condition. Now natural boundary condition is present only for the right boundary. Because of that, it will not have any contribution for the first 4 equations. So contribution is 0. For the last equation, it has contribution at the second local node of element 5. This contribution is Q0R. Now contribution will come from the essential boundary condition at the first local node of the first element. It will not be present for the other elements. So this will be 0, 0, 0, 0, and here we shall get minus K211 T11 because our Dirichlet contribution that is subtracted from the load vector. This is minus summation over B belongs to eta G K IBE TBE. So our E is 1, I is 2, and B is equals to 1. B is for element 1. This is local node 1. This is local node 2. For element 2, this is local node 1. This is local node 2, and so on. So these are the small a things. Now this particular one, this is the B belongs to eta G. So here we are getting minus K211 I is 2. We are writing the equation at the second local node K211 TB1. So this is T11. Now T11 is given as 100 degrees centigrade. K21 it is equals to minus K by delta X. And in case of the assembled matrix equation system, we already have the structure for the 4 by 4 case. So it was like K221 plus K112 plus then next K122. Remaining terms are all 0. Then it will be for the second row K212 plus K222 plus K113. Then it will be K123. These are zeros. For the third row K310, K32 is K213. Next is K223 plus K114. Then K34 it will be K124. Then K35 is 0. K41 is 0. K42 is 0. K43 is K214. K44 is K224 plus K115, and K45 is K125. If we go to the last equation, K51 is 0, K52 is 0, K53 is 0, K54 this is K215, and K55 is K225. So this is the structure for the assembled matrix equation system. If we put the values of delta X, if we put the values of K211, T11, and then the left hand side coefficient matrix, then we get the solution vector T1, T2, T3, T4, and T5 by using direct or iterative methods. So this is for NBC assembled K and F. Now, if the right hand side boundary condition it is of convective type, in that case the modification will be in the last row of the matrix. So in case of CBC, the convective boundary condition, only modification occurs in the last row of the coefficient matrix, and in the load vector the Q0R term of second vector NBC is replaced by H T infinity. It means that, therefore, for convective BC at the right boundary, our load vector is F equals to delta x, delta x, delta x, delta x, delta x by 2, 0, 0, 0, 0, H T infinity plus minus K211, T11, 0, 0, 0, 0. This is EBC, this is CBC, this is source turn. So we have assumed that Q equals to 1. So source turn. So you can take you can put Q here. So we have taken Q equals to 1 in the given problem, and because of that, the first column, sometimes we did not write the value of Q. We have simply put 1. So this is the load vector. And if you go for the left hand side coefficient matrix, this K, then in the fifth row, fifth column, we had K552. It will be K552 plus H. So we had a tridiagonal matrix equation system. These are all zeros. So the coefficient matrix is same as that of the NBC matrix, except with the augmentation of the K552 term by H. Therefore, K55 equals to K55, this will be actually K225. So K55 equals to K225 plus H. So this is the augmentation by CBC. Now, if we go for the RBC case, consider RBC at right boundary. The load vector will look like F equals to Q into delta x, delta x, delta x, delta x, delta x by 2 plus minus K211 T11 0, 0, 0, 0 plus 0, 0, 0, 0 alpha QR double dot at the right boundary. So this is source term, this is EBC, and this is RBC contribution. The matrix, it will have contribution from the nonlinearity. Okay, so this will be the basic matrix, NBC matrix, same T1, T2, T3, T4 and T5, and here for the radiative boundary condition we shall have the contribution as epsilon sigma into the fifth row, fifth column term. So all other terms, they will be zeros. This will be the only non-zero term present. Okay, and these terms will be T1, T2, T3, T4, T5 to the power 4. So this will be augmentation due to RBC at the right boundary. So we conclude today's class here. In today's class, we have solved 1D Poisson equation, subject to EBCs. We have used linear bar elements, and the results compared well with analytical as well as finite difference and finite volume solutions. We have also considered the NBC, CBC and RBC at one of the boundaries, while using multiple linear bar elements. So here I recommend the texts by Professor Hughes and Professor Reddy. Thank you very much for attending today's lecture.